The Blackbody curve.
So what you can see here is a representation of a black-body curve. Now, before we study the actual graph here, we need to quickly review what a black-body is. Now, a black body is simply an object that absorbs all the radiation that falls on it and re-emits it in the form of electromagnetic radiation.
Readmits it. That means it originates as energy and sends it out or projects it. That's important.
So in sense of stars are generating energy by the way of fusion within their core. So the light you see from stars is totally due to emission. There's no reflection going on.
Important. Emission. Projecting out, not reflecting from a sun or a nearby object.
So if you look at the black body curve, you will see that it has a very characteristic shape. Now, the black body curve actually represents basically the intensity per wavelength. So in this particular image here, we're going to be looking at the sun. You see a distribution of wavelengths and with different intensities. So on the y-axis, we have our spectral power density. So really, it's just talking about the intensity for every given wavelength. And on the x-axis, you see the wavelength. So the star that we call our sun, in this case, is giving a very characteristic curve or a black body curve. Now let's explore the parts of this graph here. So we're going to add our labels here, and you will see that what we have here is the visible spectrum. We have our infrared range, and obviously the further we go away, the longer the wavelength. And at the other end, you see the ultraviolet section.
So understanding the ultraviolet and the concept without worrying about numbers or details and the wavelengths, that's the key here. Just take the center thought.
Now, you'll see that there is quite a significant drop-off in the ultraviolet section. Now, that's not saying that the sun is not giving off any ultraviolet radiation. It is, but in terms of higher frequencies, the amount of radiation or the intensity of those ultraviolet significantly drops off. Now, the reason behind that I'm not discussing in this video, but I have a video, if you look on black bodies and Max Planck, and I'll put the link in the description below, then you can explore that. So looking at our sun, we'll see that we have a lot of infrared radiation, but we certainly have a lot more radiation in the visible spectrum. If you then look at that visible spectrum, although that we have here a differing amounts between our ultraviolet and our red, there is not a huge difference in terms of the intensities of these wavelengths. So what we end up seeing, as you can see here, this diagram up the top here, is the fact that we're going to see white light because we're getting equal amounts, roughly speaking, of the wavelengths that are in the visible spectrum. But now let's have a look what happens at the spectrum as I change the temperature. So I'm going to first lower the temperature, and you'll see what happens is we're going to get a drop of intensity along all wavelengths. But if you look very carefully, you'll find that the peak actually drops. So let me take a photo of roughly where the sun is, which is this line, and then I'm going to drop to the radiation emitted by a light bulb like so, and I press a photo here, and you can see that there is now a significant difference. So we have a drop in intensity for each of the wavelengths, but we also have a shift towards the right. In other words, the intensity of the wavelength that is of the greatest intensity is certainly moved towards the longer end. Now, the issue now here, of course, is the scale. So if I just reduce our scale of the y-axis, then we're going